I'll go ahead and introduce Mike Robinson. Mike, I saw that you joined us, and uh, we have in Mike, we have a practitioner who's involved in efforts to address both the carbon emissions cleanup job, removing the mess in the atmosphere, and some of the remediation on land, in rivers, and in the ocean. So I'm going to let Mike take it from here. Uh, there,
Thanks, Brett.
there are many folks in this space, but Mike is active in many dimensions of this.
Let's see if this is going to work. Hi, I'm Mike. um, I am kind of here in two capacities. I lead an advocacy group called PACCLEAN.org, which is this big long name, Pacific Coast Legacy Emissions Action Network. Horrible mouthful, but a good acronym. So PACCLEAN.org is a citizen-led advocacy group pushing for the development of greenhouse gas removal capacity, focused specifically on the Pacific Coast, as the name implies. And I got a few slides out of my PACCLEAN deck, and then I'm going to shift over to my other role, which is leading a company called Basic Dust that does something called enhanced weathering, which is what Brad was referring to as a practitioner. But I just thought it would be useful to set some context. So I'm going to circle back. Actually, I asked Dick if it'd be okay for me to borrow this slide and use it as a segue. So, I think that this kind of paints the picture that climate change and ocean acidification are two sides of the same coin. And they both come from this really, really bad habit that we have that, was fine when we were a tiny little band of people of only, say, a billion, but doesn't work when we're 8 billion and doing so much more of it. So, this is the problem of our times. We have dumped 2 trillion tons of climate pollution into the environment, about 40 billion tons more last year. That's causing an awful lot of problems, including acidifying the oceans. I always have to stick this in that, people talk in terms of saving the planet, and I always want to be really clear that we're not saving the planet. The planet's going to be fine without us. We're saving ourselves, right? Either we fix this problem or the planet will fix us. And this is really about saving human civilization is what it is. So we've got this 40 billion ton problem. We keep doing all of these things, and we've based our civilization on fossil fuels, and we keep dumping 40 billion tons a year, and we're working on it, right? Some jurisdictions have reduced their emissions, but there are some things that we kind of don't know how to do without fossil fuels yet, and it's going to take a while to really finally get rid of that. The scary thing, though, is this 40 billion ton problem that looks, like a really huge obstacle isn't really what's the problem. The problem is the 2 trillion ton problem. We've already dumped all this climate pollution into the atmosphere. And when you look at it from that perspective, the 40 billion tons we do every year, when people talk about getting to net zero, that's just to stop making it worse. We're going to have to talk about how do we make this better? How do we actually start to clean up our mess? And when you look at it from that perspective, it can seem completely overwhelming. And to steal from Dr. Seuss, it can seem like a mess that is so big and so deep and so tall, we cannot clean it up. There is no way at all. But, we made the mess, and we can clean up the mess. And there are a wide variety of different methods and techniques that are being explored and developed by a lot of dedicated people all around the world to figure out how do we get to the point where we're removing more than we're emitting and get into a negative emissions posture. So that's the context for this next piece. And I use the term greenhouse gas removal because CO2 is not the only greenhouse gas that we are going to need to actively remove from the environment. Methane removal is a thing, believe it or not. NOx removal is a thing now. But CO2 is the bulk of it, and CO2 is the thing that's primarily driving ocean acidification. So, a couple things greenhouse gas removal isn't. First, it is not any substitute for reduction or adaptation. I want to be crystal clear about that. We need to stop burning fossils and cap the wells immediately. we've already done a lot of damage. We're going to have to do a lot of adaptation, but we also need removals. So it's not an either or, it's not an alternative to doing reduction and adaptation. It's something we have to do in addition because we've been very slow to decarbonize. Another thing GGR is not, I think most of you know this, is the same thing as carbon capture. So you hear people talking about carbon capture, particularly carbon capture and storage. That refers to methods of reducing new emissions by capturing CO2 at the smokestack. Carbon removal or greenhouse gas removal refers to pulling it out of the environment, either the air or the surface waters. And here's a spicy take I told you I was going to do, Brad. People talk about greenhouse gas removal and say, oh, that's geoengineering. I would argue, no, it is not geoengineering. In fact, it's cleaning up climate pollution. It's restoration. It's putting the planet back the way it was when we found it. If we talk about net zero as a target, what does net zero really mean? Well, for 800,000 years, longer than humans have been on the planet, CO2 didn't go above this line. And for the 10,000 years of the development of human civilization, CO2 was in this very narrow Goldilocks band around 280. And then we figured out that we could dig stuff out of the ground and burn it and use that energy to move things. And, you know, that's been great for the development of civilization, but it has an adverse consequence that we are now very clearly experiencing. So my argument is net zero is geoengineering. We already engineered the planet inadvertently, right? Net zero is saying, oh, it's okay, we'll just leave the mess there. And we think that we'll be fine at 500 ppm because the models tell us so. We don't know that. The only thing we know is that human civilization developed during a 10,000 year period when CO2 was in this very narrow band. So all due respect to climate scientists who I have tremendous respect for, but I kind of think that we might need to be talking about getting back to something below current levels, which requires even more removal. So the one thing for sure is greenhouse gas removal is necessary just to get to net zero. It is also the only way to address legacy emissions and really get into a net negative posture. And that is a very hopeful aspect of it. Even though it's scary that we have to get really good at doing this, it's hopeful that it holds out the potential that we could raise our ambitions and actually start cleaning up the mess and make things better. So, okay, taking off the pack, putting on the project developer basic dust hat. Basic dust is a developer of enhanced weathering projects. Enhanced weathering is one of the methods of CDR. As I mentioned, you know, there are many, and I'm switching language here, by the way, to carbon dioxide removal. That is a subset of greenhouse gas removal. So when I'm doing advocacy, I talk about greenhouse gas removal. This company does carbon dioxide removal. So CDR is activities that remove CO2 from the environment and store it durably, meaning for a geological sort of timescale, so 1,000-year plus durability. And it is actually cleaning up climate pollution, which we need to do in addition to stopping making more climate pollution. And according to the IPCC, we're going to need 10 or 20 billion tons of this just to get to net zero and stabilize the climate. There is a market for CDR. Companies buy CDR credits. It's a voluntary market right now, and it's in the last 12 months. This needs to become a $1 trillion industry. And so that is also a potentially exciting aspect of greenhouse gas removal is this is a brand new industry that we can see coming and we can build with intentionality. So this creates a tremendous economic opportunity for all kinds of people. And it's rare that you can see something like this coming from so far away, to be honest. Usually with a brand new market, people will argue about whether it will get big because it depends on whether or not buyers like it. This isn't that. This has to get big. This has to get big if we want our grandchildren to have a pleasant place to live. There are mandates coming for carbon removal. And that's, I know that because I work on the advocacy side. So here's a list of policies that have been adopted or proposed. There are many more. We'll get to the point where the rule is you're not allowed to park your carbon in the sky anymore. If you're emitting, you have to actually clean it up. Enhanced weathering is one of the most promising ways of doing carbon removal or carbon dioxide removal. It is one of Earth's natural mechanisms for moving carbon from the atmosphere and the biosphere back into the geosphere. And it refers to the reaction of alkaline rocks with carbonic acid. And the result is bicarbonate that ends up in the water table and eventually ends up in the ocean, which is where we have the connection to ocean acidification. This can be done in many different places. The one that gets the most attention right now is that if you spread this volcanic dust on crop fields, you get a boost in yields. So in addition to doing carbon dioxide removal, and in addition to improving the pH of the water that runs off, you're also getting, according to a variety of studies, on average, a 13% increase in crop yields, which means this might be a carbon removal activity that we could do in large parts of the world, primarily for food security. And the carbon removal would actually be a side benefit. The other promising thing about enhanced weathering is that it's really ready to scale now. We don't really need new technology. Things like direct air capture, right now, they're incredibly expensive, and people are working hard on developing new technology to simplify it. Enhanced weathering is just moving piles of dust. We already do that, right? We're pretty good at moving billions of tons of aggregate, and this is just a different kind of aggregate. We already spread ag lime on fields. This is just a different kind of dust we're spreading on fields. So over time, we can optimize it, but it actually is kind of ready to go if we need to scale carbon removal now. I want to give you a sort of visual of it. So this is a kiloton project that we executed a couple months ago in the Willamette Valley. This is a warehouse full of waste olivine dust. This is a waste product from the making of olivine sand, which is used in steel and other industrial processes. So we took that dust, we put it in a dump trucks, we took it to the fields. We first of all, identified farmers who wanted to do this and engaged the locals in what we were going to do. Having got the dust to the fields, a spreader that's the same thing that spreads ag lime applies it to the field, and you can see, that there's this thin layer of white to light green dust on top of the field. That is the olivine dust that then gets tilled into the field, and over time, it reacts with carbonic acid in rainwater, forms bicarbonate, and that drains off. So this is the first kiloton project anywhere in the PNW. It is our demonstration project. We'll be minting credits next year with this, and then we have a pipeline of new projects for 2025. One of the other aspects of this particular method is that in addition to improving crop yields, it's going to provide a lot of rural employment, because it's just a lot of work to actually make and move the amount of dust that we're going to need to make this gigaton effective. One of the challenges is doing this on crop fields. We know that it does result in some amount of CO2 being mineralized into bicarbonate, and that some amount of that ends up in the ocean, but it's really hard to measure and prove exactly how much has occurred. You put this dust in the dirt, and as you can imagine, over the course of years, there are these complex chemical reactions going on, and you can measure, basically the way we measure it now is we measure how much alkalinity we added to the field, and then we come back every 6 months or year and we measure how much of it disappeared. And the starting point is to say, well, maybe all of that alkalinity reacted with carbonic acid and it all turned into bicarbonate and it all ended up in the ocean. But we know that that's not really what's happening, because there are other factors. So we have to take deductions off of that gross CDR potential. We have to take deductions for ways that the alkalinity could be neutralized in the field that were not related to carbonic acid, deductions for plant cation uptake. The plants will eat some of that dust. Deductions for any potential reversals that might happen on the way to the ocean, and a variety of other things. And so it's really, really complicated to measure this. And this is an emerging field that will take a few years to get more precise and more accepted about how we measure it. But it has a lot of co-benefits, and it's a very promising approach, and it's ready to go now. Measuring this same reaction, if you're doing it in water, is easier because it's happening pretty much instantaneously. So this is a image I got from a company called Carbon Run. They are doing this in acidified rivers, and their first demo project, they're based in Nova Scotia. The first demo project was with a First Nation in Nova Scotia, where they're doing this to the river because it improves fish habitat. And in the case of doing it in water, you can measure the water upstream and you can tell how much CO2 is in it or how much carbonic acid is in it. You can add then a precise dose of alkalinity and you can let that mix. You can either mix it mechanically or just let it mix in the river in this case. And then you can measure it again downstream and you can actually say, well, the water came in with this much CO2 in it and it went out with that much CO2 and more bicarbonate. And so that's the amount of carbon removal that we did. And then, of course, in all of these cases, you deduct off of that how much you emitted in doing the work. But it turns out to be that, net, this is a significant source of carbon removal. And again, this co-benefit on this is improving fish habitat, as well as reducing the acidity or increasing the pH of the water that ends up in the river or in the ocean. And this same concept of measuring it in an aquatic setting applies to many other examples as well. So it can be done in estuaries. There's a company called Vicarb based in New York that is doing this in the mouths of bays and has another installation in the East River in New York, right in Manhattan, actually. You can do it on beaches, a little harder to measure on beaches, but Project Vesta, you may have heard of, is spreading olivine sand on beaches and measuring with devices that are anchored offshore, measuring the impact on alkalinity. There's a company that's doing this on gravel roads. They're spreading steel slag on gravel roads, and that the water going through there, they're able to measure how much CDR has occurred. Coastal water facilities are an attractive possibility. So wastewater plants or desal plants or other coastal water treatment facilities where there's an opportunity to have access to a stream of carbon-rich inflow and a desire to improve the pH of the outfall. And so this is a diagram from a company called Crew Carbon that I grabbed. All of these companies are interested in doing this at coastal water facilities. And one of the nice things about this is the permitting is not going to be quite as crazy because this facility is already here. Outfall already has parameters around it, and we don't need to go outside of the existing parameters. And then people are doing it also in mines and quarries, just right at the mine. Instead of moving the dust, there's ways that you can do the mineralization at the mine. So all of these involve, in some sense, measure the water upstream, add alkalinity, measure it downstream. And since I'm talking about water treatment, I'm not sure where I'm at on time, but I know that Janine's going to want to talk about that.
Thank you, Mike. You're right on time.